You are muted, or we cannot hear you for some reason. Can you say something?
Okay, can you see my slide?
Yeah, we can see your slide on your pointer.
Okay, thank you. So thanks, organizer, for inviting me for this to speak today. So today I will discuss my recent work with my advisor Damson, and is based on two reference. And the next one, the next reference just appear today. And so the plan of the talk, I will explain again the magnetoroton in the fractional quantum Hall is nothing but it's a graviton mode. And then I will discuss that in the Dirac composite Fermi model, maybe there are more than one graviton mode. And in the last part of my talk, I will discuss how to probe the graviton modes using Raman scattering. So basically, you see that.
By the way, I think we cannot see your pointer. I thought I told you we can see it, but now we cannot see it. So maybe if you can unshare and share, I think maybe the same issue I had. Share the full.
Okay. Okay, can you see my pointer now?
Yes, it disappeared right now, but can you move it again? Disappeared somehow. I think you mentioned that if you share the.
So we know that in the fractional quantum Hall, we have the neutral excitation, which is magnetoroton, and it was proposed by Graviton, Haldane, and Plasman in 1986 as a charge density way. When you act on the ground state by the density operator, you increase the magnetoroton. And the energy spectrum of magnetoroton was derived using a single mode approximation in the same manner that Feynman derived his roton in fluid helium-4. So here is a dispersion of the magnetoroton calculated by Graviton, Haldane, and Plasman. And the magnetoroton dispersion after that was confirmed experimentally by group of Pinjuk in 1993. So here you see the dispersion duration. Let's look close to the theoretical proposal. And further than that, the magnetoroton also have like microscopic structure. And in the paper into 1992, Search and Zhang suggests that the magnetoroton, when momentum close to zero, is a quadrupole, and when the momentum close to 1/LB, you will have the dipole near the minimum of the dispersion. And basically, the idea of quantum Hall graviton was initiated by Haldane as an intrinsic guiding sensor metric in this paper in 2009, and also in the PIL paper in 2011. And we follow the idea by Haldane, and in this paper with Gorka and Cern, we suggest that the magnetoroton is a spin-2 excitation generated by the stress tensor operator acts on ground state. And now I will explain why we think that is spin-2. So here I show you the lowest Landau level conservation law. So the first equation is familiar with everybody. It's just nothing but the charge conservation. So rho is the density and J is the current. And the second equation is a momentum conservation, where here m multiplied by j is the momentum, and we have the derivative of stress tensor, and the right hand side is the Lorentz force. However, a mathematical way to go to the lowest Landau level is taking the electron mass go to zero limit, and in this situation we can ignore the first term, and with the fourth balance term we can calculate the current in terms of the derivative of stress tensor in this way. So from that you see that's the variation of density related to the derivative twice of the stress tensor in space. So that's why in this case we see that the density correlation function should go as a q to the fourth if the stress tensor correlation function doesn't have any singularity at q to 0. Okay, and we also can rewrite the correlation function here in terms of like sum over the spectrum. Okay. And so basically from that we see that the excitation when momentum close to 0 can be classified by spin. So for a spin S excitation, you see that this magic element go as q to the s when q go to 0. The reason because of the rotation symmetry. So rho is a scalar. So you need to construct a scalar from the spin and momentum. When you contracting the index, you see that this magic element will go with a q to the s if excitation has spin s. And so because of rho correlation function calculated in the Nguyen paper, you see that it go to q to the fourth. So that's why the spin of excitation should equal to 2. Okay, and from this equation, we see that with rho go to q to the fourth, then that means this magic element is non-zero when q go to 0. Okay, and so basically we argue that the magnetoroton at q equal to 0 induced by the stress tensor operator. And due to its spin 2, magnetoroton can be considered as a graviton mode in the fractional quantum Hall. And actually in the paper in 2017, Andre and Son proposed a biometric theory of fractional quantum Hall effect, in which the intrinsic metric is identified with a massive graviton excitation. And in the subsequent paper, we show that the intrinsic metric is also correspond to the magnetoroton mode in fractional quantum Hall. Okay, so the main talk, the main part of this talk, I will discuss the spin 2 modes in the composite fermion model with the filling fraction near 1/2n. So we discuss the graviton mode of the J sequence, the Zendro J sequence. Okay, so we have the composite fermion model introduced by Gorman and Fradkin with this form. And here I just add extra term for Gaussian invariant, which VI is nothing but the drift velocity calculated in terms of electric field and background magnetic field. So from this term, you see that the Dirac composite fermion has the dipole moment, and because of this, this epsilon coefficient, epsilon ij here, we see that the dipole moment of the composite fermion perpendicular to its momentum. Okay. And here we have the improved A tilde defined in CERN-Newton-Cartan formalism. So from this model, now with n, with the coefficient small n here, if we go to n equal to 1, small n equal to 1, that means we study the Dirac composite fermion model near half filling. In this case, we don't have the IDA term, and we put n here equal to 1. And here is the Lagrangian for the Dirac composite fermion near half filling. So it's nothing but the CERN-Dirac composite fermion model. And from this equation, from this Lagrangian, you see that both composite fermion and the external field couple linearly with the small a, with the emergent gauge field. So the field equation of emergent gauge field give us a constraint. So from this, we see that when you variation this Lagrangian with respect to small a naught, you see that the composite fermion density equal to the magnetic field divided by 4 pi. And furthermore, the composite fermion current related to the applied electric field. And from this model, we saw in my other work with Gorka, Robert, and Sun, we saw that this Dirac composite fermion model satisfies the particle Hall symmetry and also reproduce the expected result of electromagnetic response. And now we see that the low energy degree of freedom of this Dirac composite fermion model as a multipolar deformation of the Fermi surface, of the composite Fermi surface. And here is a figure that I borrowed from Andre in many of his talks. And because of the Dirac composite fermion density is fixed by the applied magnetic field, and the composite fermion current fixed by the applied electric field. So that's why the dilatation mode and the translation mode of the deformation of Fermi surface is non-dynamical because it's constrained. However, you can have all other higher deformation of the Dirac composite Fermi surface. And basically in my paper with Andre and Sun in 2018, we saw that the biometric theory mode correspond to the shear deformation and with the spin 2. And so we identify that the emergent the emergent degree of freedom at low energy here has a spin 2, and it's a magnetoroton, and it's nothing but it's a deformation of Dirac composite fermion surface, the shear mode. Okay. So now we come back to the model with the Zendra small n. So when, for example, for 1/4, 1/6, or 1/8, and tetra, and we consider the gene sequence with this 2-gene sequence with this filling fraction where big N going to infinity is very large. Okay. And with this filling fraction of the gene sequence, we already know the Wendy ship calculated in this paper by Andre, Cho Yu, Sasha, and Edward Fradkin. And here is the equation that determines the Wendy ship. Okay, and from this Dirac composite fermion model introduced by Gorman and Fradkin, we can calculate the projected static structure factor, which is nothing but is equal time density correlation. And we see that with this definition, you will get the value of the coefficient. S4 is the coefficient of Q to the 4th in the projected static structure factor, and with this form. Okay, and there's one issue that happened here. So Haldane in some paper suggests Haldane bound for the S4 of the static structure factor, and we see that with this result of the static structure factor calculated from the Dirac composite fermion model, we see that it violates the Haldane bound for the filling fraction nu plus here. Okay, so with n bigger than 1, then you see that you violate this because the result here is smaller than the right-hand side. It's not the problem of the Dirac composite fermion near half filling with small n equal to 1, because at this time this sign will be the equal sign, so it's not the problem. Okay. And now, motivated by the argument on the density correlation function and the spin of the excitation, we see that we need more contribution to the Q to the fourth term of the density correlation function to satisfy the Haldane bound. So from the previous argument about the spin of the excitation, then we need more spin to most. So we have more graviton. Okay. So to do that, we add more spin to mode to the effective action, and we call the extra spin to mode as Haldane sector due to Haldane initial idea of preserving deformation of the elementary droplets. However, the theoretical model of the extra spin to mode follow closely the biometric theory by Andre and Son. Okay. And in the biometric theory formalism, we consider the extra degree of freedom, which is immersion view by, and from that it's also the view by also can define through the new immersion matrix. Yeah, so this is the idea introduced by Andre, and from that we also have the inversion view by and define the spin connection, the immersion spin connection in the usual way. Here, this is nothing but it's a covariant derivative defined the same manner in the GR with the matrix GHIJ is nothing but it's the immersion matrix. Okay. So here is our proposal for the Lagrangian of the Haldane sector. So the Lagrangian of the Haldane sector have this form. So A is the background magnetic field, but the background gauge field, and omega hat here is nothing but is the immersion spin connection that we defined in the previous slide. And this Lagrangian is nothing but is a leading order in the derivative of the Lagrangian biometric theory that introduced by Andre and also Son in 2017. Here we have a few constant. We need gamma smaller than 1 so that we are in the isotropic phase of the fractional quantum Hall, and m tilde is also positive and constant. However, the important coefficient here is a single unknown zeta. Okay. And basically, the last term here appear because of the time component of the spin connection. We go with the combination with the extra term here is the vorticity of the deep velocity here. And basically, we need to emphasize that there's only a single unknown in this Lagrangian, and we need to find the single unknown here that is only depend on small n. And now with the full theory, including the composite fermion sector introduced by Raman and Fradkin, we add the Haldane sector here, and we calculate the Wenzel shift directly from this action. And we see that the Wenzel shape has this form with the eta for both mu plus and mu minus. Now we compare with the known result for the Wenzel shape of the gene sequence. We see that if zeta equal to n minus 1, we get the expected value of the Wenzel shape. And you see that near half filling, when n equal to 1, you see that zeta equal to 0, then that means we don't need to consider the Haldane sector. And from the full theory, we also calculate the static structure factor, and he's a form of the static structure factor, including the new term zeta. It's a contribution of the Haldane sector to the static structure factor calculation. And again, if we choose zeta equal to n minus 1, the static structure factor satisfies the Haldane bound. So the new plus, we saturate the bound, but the new minus higher than the bound, but it's also okay. So in the previous slide, I showed that if we don't have this zeta, then basically the S4 of new plus will violate the Haldane bound. And we also calculate more physical result with the new theory, and we saw that we can reproduce expected Hall viscosity. Well, of course, because we have the correct Wenzel shape. We also show that the Hall conductivity satisfies the relation between the finite momentum Hall conductivity and the Wenzel shape with this form. Yeah, so basically for both nu plus and nu minus, we have this equation satisfied, where S nu is nothing but the Wenzel shape and G is a G factor equal to 2. And this relation was proposed by Carlos and Son in 2011. So the result here suggests that our model satisfies Galilean invariant. From this model, we also obtain the long wavelength version of GMP algebra. So the commutation duration of density with different momentum satisfies this equation. It's nothing but it's the long wavelength limit of the GMP algebra. And we need to emphasize that the dipole moment term that we introduce in the Dirac composite fermion model is a key ingredient to obtain the GMP algebra. So basically, we can show that on the physical result that I showed you before, preserve if we have more than one extra spin 2 mode. So for example, if we have K extra spin 2 mode with a coupling zeta I with background field with this form, we see that on the previous result satisfy if you have this condition for the coupling of the extra mode. And so one of the main conclusions of this talk is that we have the additional low energy. So in addition to the low energy mode of spin 2 mode, which is the deformation of Dirac composite fermion Fermi surface, we have extra spin 2 mode with higher energy. And so we have more graviton mode in the fractional quantum mode. And also from the calculation of static structure factor, we see that the new minor state doesn't saturate the Haldane bound. So that suggests that the new minor state isn't chiron. So we will have more than one spin 2 mode and with different chironality. And basically the last two statements are confirmed numerically for nu equal to 27. in the private communication with Duncan, Ed, and Nguyen. And let me take my chance to thank Ed to show us the numerical results that support our proposal and give us confidence to publish the paper. So in the last part of my talk, I will tell you how to probe the graviton using the Raman scattering experiment. So here is a setup of the Raman scattering. You have the sample here, the quantum Hall sample here. You size laser in, and you measure the scatter photon. And from the momentum conservation and the energy conservation, we can have the momentum of the excitation mode and also the frequency. So by measuring the scatter photon, we can have the dispersion relation of the magnetoroton mode. And in the previous theoretical model by Flatman and he, the scatter light intensity supposed to measure the dynamic structure factor. It's a density correlation function. However, you see that the static structure factor go to Q to the fourth. And that means this theoretical model cannot explain the peak at zero momentum in the Raman scattering experiment. So together with CERN, we propose a new model. So we study the model of photon coupled with both light hole and heavy holes band and also electron band. So we suggest that the photon come in, we excite the electron and hole pair. So electron here go up to the conducting band and give us the electron hole pair. And after that, the extra electron will go down and emit the photon. So leave us roton excitation on the conducting band and give us back the full field hole band. And in the setup, we consider the resonance scattering, where the frequency of photon should be very close to the energy gap between the conducting band and valence band. And after that, we perform the second order perturbation theory by integrate our own of the whole band, and we introduce the effective coupling of the photon electromagnetic field to electron in the conducting band with this form. So TZZ and TZ bar Z bar here is nothing but it's the stress tensor in the conducting band, and E here is nothing but it's the electric field of photon. Okay. And here we have two terms. And the first term is rotational invariant, and it's dominant. And the second term, we have the small term that violates the rotational invariant due to the broken rotational symmetry of the Luttinger model for the whole band. And in our effective model, we show that the scatter light intensity measures the set tensor correlation function instead of the density correlation function. So that means the model that we have proposed explains the peak in Raman scattering near momentum equal to 0.
Sung, how much longer do you think you need?
I think only if I have only 3 more slides and basically only 3-4 minutes and I can finish.
Okay, maybe if you could try to finish 1 or 2 minutes.
Okay,
I think sure. It's fine, maybe because you can use some time of the questions.
Yeah, sure. Thank you. And basically, we also propose that using Raman scattering, you not only can measure the dispersion duration, but you also can measure the currently of the spin 2 mode. So if we say that spin 2 excitation is spin 2, if the z direction of the spin with the same direction with magnetic field, and you say that is spin -2 if the spin in z direction is in the opposite direction to the magnetic field. And basically, we think that excitation will be induced by the action of the two components of the stress tensor, TZZ and TZ bar Z bar. So that creates the spin 2 mode, and this one will create the spin -2 mode. And here we define the zero momentum of TZZ and TZ bar Z bar and T and T bar. And from that, we have the definition of the two spectral functions. Yeah, just summation over the excitation. And with the circular polarized Raman scattering near Q equal to 0, we saw that this experiment, the scatter line intensity will measure the spectral function of TZZ. And with this opposite polarization, the scatter line intensity will measure the spectral function of the TZ bar Z bar. And we see that if the magnetoroton has the spin 2, then in this experiment we see a peak, the strong peak in this side. And if the magneton has the spin -2, then we see the strong peak on this side. So for the current state, we see that the result will dominate by one side of photon spin flip. So either this side or this side, we see the strong peak. And from that, we can show that if we measure the spectral function here, we see that if we have more than one peak at a different frequency, and we can say that we have more than one graviton. And let me go to my conclusion. So in this talk, I show that magnetoroton is a massive graviton, and we have extra graviton in general Jane sequence near 1/4, 1/6, or in tetra. And the graviton can be probed using the circular polarized Raman scattering. Thank you.
Thank you. I clap on behalf of the audience. Yeah, so now questions for both Sung and Lauren, please raise your hand.